good. Okay, let's get into it then. So let's get started into this Leetcode problem. Thanks for joining, everyone. Today's problem is going to be we're going to do a medium Leetcode, and depending on how that goes, we might do a follow up or a different question as a second question kind of thing. And so yeah, right now it's 3:06. We're going to try to end at 4, and with a 50-minute implementation time, that means we're going to be targeting 3:55 for your reference. Time management.
Okay.
Okay, so the first question is going to be about a island question. So essentially,
Mm-hmm.
we want to given a m by n 2D grid, okay, and this grid is going to be it's going to be a binary grid, okay, so it's only going to be zeros or ones numbers, or whatever type you prefer. We can just say zeros or ones, make it easy, okay,
Okay.
and you're going to return a number representing the total number of islands. Okay, so an island is defined by contiguous portions of ones. Okay, and it's only considered contiguous if it's connected on the Cartesian coordinates, so north, east, southwest, up, down, left, right. Okay, so diagonal connections do not count.
Okay. Got it. Yep. Is that it for the description or?
Yep, that's it. Feel free to ask questions.
Okay. So yeah, I was just taking some notes as you were speaking, but just to clarify that I understand the problem. The input to the problem is an m by n 2D grid of binary values, either 0 or 1, with sorry, I didn't catch this part, but does 0 represent what does 0 and 1 represent again?
Yeah, so if you're doing the island analogy, 0 is water and 1 is land. But you're basically just trying
Okay.
to find the number of consecutive or contiguous groups of ones, essentially.
Okay, got it. So 0 equals water and 1 equals land. And we are supposed to return the number of islands in the grid. And the definition of an island is a group of cells that are connected via the Cartesian coordinates north, east, south, and west. Does not include diagonal connections.
That's right, yeah.
Okay, cool. Okay. Let me think about this. So we're after the number of islands.
Yep.
Okay, so just thinking out loud here, the first thing that comes to mind is we could iterate through the cells of this grid until we find a land cell. And at that point, we will try to find all land cells that are part of that island.
Okay.
And then once we do that, we increment the island count by 1. And then we continue on with our iteration. And then we just we do that for the entire grid, at which point we will have calculated the total number of islands, and then we will return that number. One thing that I think I need to consider is I don't want to be visiting like land cells more than once, because that could lead to duplicate counts. So I'm thinking there needs to be a way of um, marking a island as having been visited,
Okay.
so that like we don't like revisit again, and that would like mess up the total count. Um, so one solution to that is to mark a like use some kind of like marker character to indicate that that cell has been visited. For example, we could use like an asterisk. Um,
And where's this asterisk going to be stored?
it could be stored like in the original grid.
Okay. What if we can't
Yeah.
modify the grid? Let's put that restriction on.
Okay. So if we cannot modify the grid, it has to be. We have to keep the input as is. Then, hmm. Um, yeah, one thing we could do is just like store the coordinates of the cells that have been visited, and then determining whether a cell has been visited is just as simple as just checking. Um, I would guess it would be a set of coordinates, checking that set to see if this coordinate has been visited or not.
Okay. Yeah. Okay.
Does that sound reasonable?
Yeah, that makes sense.
Okay, cool. So I think that's the high-level idea of how I want to implement this. Can I start implementing?
Yeah, that makes sense. Let's go for it.
Okay. Okay, so I'm calling this function public. It's running an integer num island. And this is taking I guess it could be a character array of, let's call this island. And we're returning just, I'll just write 0 for now. It's obviously going to change. Okay, so I mentioned earlier that we need a set of coordinates to keep track of cells that have already been visited. So this could be a no, I think there is a built-in type called pair, which works well here because a coordinate is literally just a pair of numbers, right?
Yeah, sure.
So this would be visited cells.
Okay.
And it's going to be new hash set. Um, should I worry about imports or
No, you don't
just
have to. Java doesn't actually specifically have a pair depending on what version of Java you use.
Oh yeah. I remember running into that. I remember running into that problem
You should use
a while
generics
ago.
here though
Yeah.
for the hash set. Yeah.
Okay, and then there's gonna be like a running count of number of islands. So count, and it's gonna be start off at 0. Oh, and one. Okay, so I'm just realizing now that one thing that I didn't go into detail about is how we're actually gonna like determine which cells make up a single island. So I think we could use like a recursive like depth first search method.
Mm-hmm.
And in that method, what we'll be doing is um, given a cell, like we're going to be starting off on a cell that's bland, and then we're going to look at the four neighbors of that cell, and then counting the number of and then just like marking each of those neighbors, and also like neighbors of those neighbors, etc., um, as having been visited. So basically, if we're at a land cell, we need to recursively mark all the cells that are connected to this cell, uh, or like add those cells to the visited set.
Yeah, that's right.
And basically just you can use like any type of like recursive method for that. But the first thing we'll do here after we set the count to 0 is iterate through the grid itself, checking each cell, checking for land. So um, Okay, so the thing we'll be checking for is if this cell is land. Um, so so this equals a 1, then that means we need to initialize our traversal here. I'm just going to call this method DFS for now, and I'll implement it as a helper method later.
Okay.
So this will take in the island. It'll take in the current coordinates. Yeah. And then after we're done with this traversal, we need to increment the counter by 1. The work of actually adding the visited cells to this set will be done in DFS, which means that we actually need to pass this. We could pass this into this function, or we can just like set it as a class level variable, but I think either is fine. I am just going to pass it in.
That's fine. Yeah.
Visited. Okay, so once we do that, we increment the count by 1, and then we continue this iteration until we're done with the entire island, at which point we return the count. Oh, not return count. Okay, so next thing we need to do is implement DFS. Okay, so this will be private void DFS, and then it takes in the island int. This will be the row, and then also take in a column, and then it will also take in the sets of pair of integer to integer. Okay, so depending on like how I want to implement this, I might need to do like some bounds checking right off the bat to make sure that the cell we're currently at is actually exists in the island.
Okay.
So if we do it that way, then yeah, that's the first thing we need to check. So if it's out of bounds, then we just return right away. So basically, if row is less than 0, or column is less than 0, or row is greater than or equal to island dot length, or column is greater than or equal to island index at 0 dot length.
Okay. Yep.
Then we return right away because we're off the grid.
Okay.
Okay, the other thing we need to check is if this current cell that we're at has already been visited. Then we just we stop the iteration. I mean the traversal right away.
Okay.
Actually, this could be like grouped into this giant if statement as well. So if visited cells dot contains, oh, I'm gonna have to create a new pair because I currently only have int and call.
Yeah.
Huh.
Do you know how to create a pair?
Yeah. So I think I could do that here too. because I'm gonna have to do it like later on anyways. I might as well do it like before this statement. So for, if this contains the current coordinates, then we return. Okay, so next is we need to traverse the neighbors of. Actually, one thing I forgot here is we also need to check. We could check in this giant if statement if the current cell actually is like land or water, because if it is water, then we also need to stop the traversal as well. That's another thing we could check here.
Mm-hmm.
So if island row call if it's equal to water, then we stop the traversal right away.
Okay.
Okay. Otherwise, we know that we are on a land cell that exists in the grid and also hasn't been visited. So in that case, what we need to do is we need to first of all add the current coordinates to the visited cells set.
Okay.
And then after that, we need to traverse the north, east, south, and west neighbors. So north would be row -1 call, and then oh shit! I just realized I have to do a lot of typing here. I'm just gonna type the redundant variables first, and then add the
Sure.
changing ones. So it'll be, the redundant variables are gonna be like island, and then visited cells, and then I'm just gonna copy this 4 times before adding the other variables. So, oops. Okay, so north would be row -1 column.
I think your argument order is a bit off there.
Sorry?
The order of your parameters.
Oh, okay, right. I'll set this as the second parameter.
Yeah, I guess that works.
Okay, so that means I also need to do it here. Okay, and then for that's north, and then north south is row +1, and then column. East is row, and then column -1, and then west is row, and then column +1. Okay. Yeah, so once we visited, like we've done the traversal in all 4 directions, we have fully explored this island.
Okay.
So we would be done with this island, and then we can just return it. We just return. Alright, so it's the end of the function, so we don't need to explicitly write return.
Okay.
Okay. So I'm just gonna like run through everything again to like check if there's like any errors here. Or maybe one thing I could do is like I could like run through an example test case on the code that I've written?
Yeah, you can do that too. That makes sense.
Okay, so I'm just gonna come up with like a random a random island. Gosh, this might take a while to actually write. But...
You can use this one.
Oh, you have one. Okay, great. Okay, so this island should have. I mean, this rig should have one, two, three islands, right?
Yep, 3.
Okay, so we pass into this into num islands. What will happen? So um,
You're a bit
okay,
quiet. Did you
first
did you
rig.
did your mic move away?
No, I
Oh,
actually didn't change
okay. No,
anything.
no, you sound good now.
Is it better
You
now?
sound good now.
Okay. Okay, so the first cell is an island, so we'll start DFS right away. Um, so what will happen in DFS? Well, this is definitely in bounds and it has not been added to the set yet. So we'll just do DFS on starting from here. It will check in all 4 directions, but only the right and downwards directions are legitimate. So it will then go to does east come before west? So south comes before west. So it'll go to this cell, and then it will go to this cell, and then it will go to this cell. And I did remember to add visited cells to the set, right?
Yeah.
Yeah, right here, line 29. So that should be fine. So once this one is visited, these cells in this island would have already been added to the visited set. So once we go back to the main function, we'll be at the second cell in the first row, but this will have already been visited, so we don't call DFS here, and like
Sorry, can you say
so
that
on
again?
and so forth. Yeah, so since the cells of the island in the top left corner have already been added to the visited cells set,
Yeah.
they will not be visited again in the main function.
Can you describe why that
The,
is?
um, oh, sorry, I think I misspoke there. Like DFS will still be called, but it'll just return right away because visited cells already contains all the cells in this first top left island here.
Yeah, I agree. And what happens to the
Yeah,
count in
yeah.
that case?
What happens? Oh shit, that's actually a good point because it will be incremented again, even though it shouldn't be.
That's right.
So I think what should happen here is we should actually do a check here right away to make sure the cell hasn't been visited to prevent that.
Yeah, that makes more sense.
Dang. Whoops. Okay. So this visited does not contain. Oh, I guess we have to make a new pair here. Uh, and waste a little bit of memory. Shit. No, IJ. It'll be... Only if the visited set does not contain the current coordinate, then we do DFS.
Okay. Is that meant to
Yeah.
be or?
So I totally brain farted. There should be an and.
Okay. Okay.
I think that.
Okay.
Should be correct now.
Okay, yeah, looks good to me as well. Let's go through the time and space complexity for your implementation.
Right. Okay, so in terms of um, time complexity, so in the outer fun or like the main function num islands, we're visiting in each cell once. Um,
Mm-hmm.
and then in DFS, um, okay, I want to say I want to make a statement here. I'm not 100% sure if it's correct, but each cell will be visited. It will be visited a at most um at most 4 times because say we could have like a cell say it's the cell that I'm highlighting here
Sure. Yeah.
in it'll be visited like it could be visited from the left, right, top, or bottom. But once it's visited from the left, like it's not possible to visit it from the left again because that cell will already have been added to the visited cells set. So because each cell will be visited a constant number of times, the overall time complexity would be it would be the size of the island, which is m by n.
Okay.
And then in terms of space complexity, the thing that we're storing that depends on m and n is the well actually I don't know if it depends on m and n, but visited cells is the auxiliary data structure that we're storing, and that depends on the number of cells that are land, which I guess could be at worst it could be all the cells could be land, in which case we'd be storing m by n.
Okay.
Another thing to consider is um, DFS, which is a recursive function,
Mm-hmm.
and so the space complexity of that depends on the depth of the call stack. Um, so let me think about that. What could the maximum depth of this call stack be? In worst case, I think it could also be m by n.
Can you explain why
Like
n
it
by
could
n?
be, yeah, if we have like um, if our grid is like very if it's like one by something or something by one,
Mm-hmm.
um, then in that case, um, there's a possibility that we need to visit like every single cell while traversing the current island.
Is that the connection there's not clear? Why is it that needing to traverse every cell, which I agree with, why does that necessarily mean that the call stack will also be n by n? That implication is not clear.
No, I'm just coming up with like a case where that would be the case. Like if we have
Yeah, yeah,
like a skinny island, right, where it's like one by like some number,
I agree.
which is like greater than one or something.
Is that generally
Like
true even if
in
it's not
that
one?
case, sorry.
Is that generally true even if it's not one by n but m by n?
I'm okay. I wanna think about this for a bit
Okay.
before saying yes or no. Okay, so mm, so this function first prioritizes visiting the northern cell, the cell to its the cell that is above it,
Mm-hmm.
before going to any other cell. So in the worst case, just looking at this the first call to DFS, at worst, it'll traverse the length of the entire column, which is m, before
Yep.
moving on to the next one. So the second call to DFS, it will traverse the entire all the cells to the south or bottom. And in the worst case, that would also be the entire column. Similar sort of thing for the next two calls, except it would be traversing the entire row.
Mm-hmm. Yeah.
I'm just trying to think like what that does to the overall time complexity of, the overall space complexity of DFS.
It's a tricky question.
Yeah, I know. Oh gosh. Okay, so this the second call on line 31 to DFS will not happen until the first call is like exhausted.
Do you mean these two calls? Because there's two calls.
Like the first call to DFS will continually be called until it's not possible, until like we're out of bounds basically, or
Until
like
yeah,
it's not possible to call DFS anymore.
Yeah.
At which point we will start calling the second call to DFS. So in the worst case, there will be m calls to the first DFS before we start calling the second DFS. Same thing here. Like at worst, there will be like m calls to the second DFS before we start calling the third DFS. And then at worst, there will be n calls to the third DFS before we start calling the fourth DFS. Okay, but what does that say about the overall space complexity? There could also be a case where like we make one call to the first DFS and then like a call to the second DFS. Like it's not guaranteed that we'll only be calling the first DFS until we can't anymore.
But it is
But
guaranteed,
the overall
right?
like the overall like call stack doesn't end until like we visit the entire island.
Yeah.
I'm just thinking like in the case where like the entire island is filled with land.
Yeah.
Like what would a call stack look like? I think the call stack would be of size m times n in that case. That's my intuition, but I'm just trying to explain why.
Okay, we can revisit that. We can revisit that. This is gonna take too long
okay.
at this point.
Okay.
We have about 10-15 minutes, so why don't we? So I'll ask a follow-up question about this problem.
Okay.
And a follow-up question adds a bit of complexity. Okay, so first of all, let's assume that the implementation currently is correct. Now I'm going to introduce a second grid. Okay, so second grid. So the first grid, you can call it grid 1, or islands, whatever you want to call it. The second grid is also similarly, it's the same. It's another grid of islands. Okay, so it's another m by n grid. It's the same dimensions, by the way. So it's the same m by n grid, 2D grid, binary values 0 and 1. Okay, and so the second grid also has some number of islands. Okay, now in this new function we want to return, in this new function we want to return the number of islands in the second grid that are wholly contained by an island in the first grid.
Oh, okay. Okay, so we want to just to like just to reiterate what you said.
Yeah.
We want to find the number of islands in the first grid that are wholly contained by an island in the second grid.
Other way around. But yeah.
Other way around.
Yeah.
Okay, so we want to find the number of islands in the second grid
Yes.
that are wholly contained by an island in the first grid.
That's right. Yeah.
Got it.
In other words, we want the number of islands in the second grid, or just the number of wholly contained islands in the second grid, and we'll define an island as wholly contained in this case if every land coordinate of that island in the second grid is also land in the first grid.
Okay. 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 I think I understand the problem. Just for example, if like this is an extreme example, but if the first island was like all land,
Yep.
and then the second island was the island shown in the example here.
Yep.
The answer would be three, right?
That's right. It would be three. Yeah.
Okay, but if the first island contained only let's just say all ones in the third row.
Okay.
And the second island was is a given island in Maine. Then the answer would be one, right?
So I didn't follow the second example. So in the second example, you say so this is grid one.
This is grid two.
This is grid two.
This is grid two.
Okay, and then
yeah.
And what was
so
grid one?
If grid one was just the third row filled with ones,
and all else was zeros.
All else was zeros.
Yeah, then it would just be one because it would only be this island totally contained.
Okay, I think I got it. Okay. Okay, interesting. Just thinking off the top of my head, one thing that we could do is just keep track of the islands that are in the first grid. What I mean by keep track of is like for each island, have a set of the number of cells that are contained in that island.
Number of cells.
So of the cells themselves, maybe like using a set or some other like collection.
Okay.
So that would be for each island, and then there'll be like some like way of some algorithm to do that, and then once we have that, we will look at the second grid, and then do like the same process, like find all the islands in the second grid, and then what we'll do is like for each island in the second grid, we will like somehow check each island in the first grid to see if it's contained in that island, doing like some kind of modified like set comparison.
Okay.
And then from there, we should get an answer.
Do we actually need to count the islands in the first grid?
Do we need to count the islands? Oh no, I don't think I'm not counting the islands in the first grid. I'm just like storing the cells of each island in the first grid. I'm not like counting.
Okay, I see what you mean. How is that different? Like if you were to store, for example, you're saying store all these cells of a given island in grid one. How's that different from just the grid itself, which tells you if a coordinate is land or water? Like what do you benefit from knowing the coordinates of a specific island?
Oh right, I see what you mean. So I believe, like, if I'm not mistaken, one of the requirements of the question was that we need we need an island in the second grid to be wholly contained by an island in the first grid.
That's true.
So what does that imply?
Well, what I'm implying here is that knowing that all the islands, knowing what cells an island contains in grid one is not actually necessary because the counterexample you're trying to think of is what if it's contained by two islands in grid one, right? That's not possible because then there would be that means that the two islands do not wholly cover the grid two island because otherwise it'd be one island in grid one.
Yeah, yeah. Yeah, that's true. So if we don't need to like keep track of like the islands in grid one, um, one thing we could do is just basically for each island that we find in grid two,
Yep.
just basically check just check if like all those cells are ones in grid one.
Yeah.
And, wait, is that all we need to do though? Because there's a requirement that we like the cells cannot be diagonally connected. But if an island if we find an island in grid two, the definition of island is that cannot be diagonally connected. So
Yeah. Yes. Yes.
yeah, we can just do that. We just basically find all the islands in uh, grid two, and then for each island, check if the cells of that island and island one are all ones. And if it is, then we know that the island in grid two is wholly contained by island in grid one. Yeah,
Yeah.
I think that's what I would do if I. I know we're running out of time, but
Yeah.
if I had time to implement, that's what I would implement.
Yeah. Okay. That sounds good. Um, yeah, we're bad at time, so we won't be implementing that. And let's just call it here, and let's go through some feedback for it because I think there's some to talk about in terms of the time and space complexity there.
Yeah.
Cool. Then yeah, let's just start off with how you felt with your solution.
Um, yeah. So I think I had a good intuition of like how to go about solving this problem.
Okay.
It would the main challenge was actually just like the implementation details of this problem. I had like the main idea like pretty quickly, but um, like I think I remember like I forgot that I needed to like check the visited cells array. I mean the visited cells set
Yeah.
first before like diving into the traversal, which something an oversight on my part, which would have resulted in incorrect solution. I think other than that, I felt pretty good about the implementation part.
Okay.
I think that I had a hard time like justifying the space complexity of the function though.
Yeah, we can talk about that.
I have an intuition that it is m by n, but I wasn't able to like explain it well.
Yeah. Yeah, it's not easy to explain. Okay. Yeah. Let's
Like, I think
let's.
time complexity I was able to explain, but then space complexity I had like a much more
Yeah,
difficult
I know
time.
for sure. Yeah. Okay. Yeah. Let's talk about that. So the first thing, start from the top, right? There was some good stuff in terms of, like, there you had a pretty, I agree, you had a good intuition about how to solve these kind of problems. One thing I will say just off the bat though is that like there can definitely be like you spent a good amount of time at the start with the clarification, right? With forming an idea, right? And then
Mm-hmm.
kind of getting alignment there.
Mm-hmm.
If you think that you're gonna be spending time to make a follow up example anyways, or not a follow up, an example input to test, this is where you should have
Uh-huh.
done it.
Oh,
Okay,
okay, I see what you mean.
so
Because I think I ended up doing it like after I
yeah,
had
exactly.
implemented the things.
Right. So basically, when you made the example at the end, you reaped none of the benefit of having that example to look at when you're coding it.
No, that is a good point. Yes.
Okay. So yeah. So that's the first thing. Otherwise, like in this case, I think he actually got the problem pretty well. So I don't think that's too big of an issue. But this is something which you could definitely like. This is something you could definitely kind of work on in the future because again, there might be a problem that you don't have that intuition about, and then yeah, it will definitely help you if if it ends up going that far, right? Um,
Mhm.
okay, so yeah, so that's the first thing. One thing I will also say is uh, the setup was pretty good, and you had high clarity before kind of proceeding, and I think that's kind of why you were able to finish it pretty quickly. So by like 20 minutes, 25 minutes into the implementation, you basically got down all the details. Again, right, there were some small things you missed that affected the correctness, right? So the check I mentioned
Yeah.
before, um, in terms of preventing that stuff, because it seemed like a lot of this problem, the bulk of it was in the DFS, right? That doesn't mean you
Yeah.
still got to keep in mind that like the correctness of everything around it is still really important, right? And so
Yeah.
one thing you can write to yourself to kind of remind yourself, and you can to also kind of tell the interviewer your intention for the future, is to state out the invariance, right? So for example, the count here will only be incremented once we visit a new island,
Oh, right, right. A
right?
new island
Right?
keyword.
So and so
Yeah.
one way you can, for example, one way you can be, depending on the difficulty for this problem, I don't think it's necessary, but depending on the difficulty of the problem, you could go as far as to say, like, for example, for this piece of code, right? You could say, um, if if next chord is new, ij, like you could do this, right? And then that way you're forced to implement this helper function the way that you originally intended, right? So for example, if you had implemented this originally without considering the visited cells, right? Now when you come
Mhm.
back to it and you need to implement the next coordinate is new, it would make sense. Oh yeah, right. I also need to now check the visited cells because otherwise it wouldn't make sense otherwise. Right.
Mhm.
So this is one way you can be a bit more explicit about it. I think generally speaking, the problem of this difficulty is just because you forgot. And so it's up to you to
Yeah, yeah.
determine, did you forget, and it's a systematic thing. If it's systematic, then you should force yourself to be more correct by writing helpers like this,
Yeah.
right? But if you think it just slipped your mind, and I hope hopefully that is the case, then yeah, just be more careful about that, right? But this is a
Yeah, I
system
think
you can use
there's a
to kind of safeguard
yeah.
yourself.
That is a bad habit of mine of like where I blame Leetcode shifting responsibility to the platform where I if this was like Leetcode, I would just rely on the submit button or something to catch this error. But I think that's a bad habit because uh, the submit button is not always there. It's never there in interviews. So
Yeah, yeah, it's
I then
important.
just like resist the temptation to like press the submit button and instead just like look at my like review the code again, um, as if it was like a code review and like a as if it was like a code review
Yeah,
rather than just relying on the submit button to be my code reviewer.
yeah, I agree. Right, it's important also because, and it's also it's not only that you have to review it and catch a mistake. It's also, I'd say, relatively important to get it right the first time around, because when you first wrote that line of code, you had already decided on the implementation idea, right? It's not because you added visited cells later that it was incorrect. No, you always had it, and it was never correct, right? That's an important distinction
Yeah,
because if, for example, this was the second question of the interview and there was no time to go through the details afterwards, this will just be marked straight up wrong because you have misunderstood the purpose of doing DFS, right? So
yeah,
it's
yeah.
important. So this is right. So writing the helper is another way to kind of safeguard your intention, but just keep that in mind.
Mm-hmm.
Okay, what else? Let's see. So DFS implementation was pretty good. One is that when you said this, you said it backwards. You said column -1 was east, and you said column +1 is west. That's technically backwards,
Oh, right,
but
right,
it's not a big deal. It's still correct. Okay, now let's talk about the time complexity. Right. So time complexity. This is pretty trivial. This is indeed n by n. That's not very, because you have to traverse everything at least once. Um, and I think one thing which, and okay, the space complexity. This is the part which I think is a bit more tricky in the sense because the way that you wrote the DFS did not help you visualize the situation. And what I mean by that is that you are checking, you are checking reactively instead of opportunistically, right? So even if row -1 becomes invalid, you still add this to the call stack. Okay,
yeah.
and so that makes thinking a bit harder. However, the way I would recommend you think about this, kind of size is if you're checking like reactively, just imagine that your grid is m plus one by n plus one, right? Then it's identical. Um, the the difference there really is like, for example, if you're checking opportunistically instead, you would only like queue this onto your call stack if row minus one call is valid. Okay, so that's like the other way around to do it. Now this is more clean code, so that's why I know why people prefer this method, but this is just a distinction you should keep in mind because that might help you think about things. Okay, so how do we count the recursive maximum depth of DFS? Right. So for example, you were right. So let's say we're just in some like let's just say for the sake of argument, we're in the middle of the grid, right? And
Mm-hmm.
there's no visited cells. Just so we can go through the iteration, right? So
Mm-hmm.
if you're in that case, that means you will be going row minus one, so north, right? You'll be going north continuously until you hit
Yep.
the edge.
Are we assuming the island is like all land?
Yeah, I
or...
assume it's all land right now, just for like
Okay.
maximum complexity, right?
Okay. Okay.
So you would go north until you hit the edge.
Yep.
Right. The question here is, at this point, how big is your call stack? And the call stack size here, do you have intuition for that?
Yeah. So it could be up to number of rows.
Correct. Right. It could be so.
Which is m.
Yeah. Right. Exactly. So the maximum call stack, if you were only to go up and down, obviously it's not realistic, but if you only had these two calls, right,
Mm-hmm.
is let's just call it m. M is the number of rows, right?
Yeah.
That makes sense. And the reason that's m and not like m by n or something else is because you only on queue a constant number of left and right columns. So you're not expanding the left and right columns. You're just on queuing a fixed number of them,
Mm-hmm.
right? And what's the opposite condition? The opposite condition is if you're going just rows. If you're going in a row, you're going left and right. Okay, like if you're going left and right, then what's your maximum complexity for time? For space.
For space, the depth of the recursion stack would be limited by number of columns, so which is n, and then you'd be making a constant number of calls to north and south. So then it would end up being just O of n.
Yeah, it would be O of n. And so what that means essentially is, but like, okay, right. So that's the idealized case, right? Essentially this is like the 1D case you were talking about before, right?
Yeah.
I think the detail here is if you are increasing the, and this is the base case, right? So the base case, right, is basically the maximum of m or n for a low dimensional what the hell do you call it? For a low dimensional matrix. That's what it's called.
Yeah.
All right. And so when you grow the dimension, the assumption that breaks is that you on queue a fixed number of the other dimension, of the other direction, right? Because now every time you on queue one of these other directions, that's going to get popped off the stack eventually, and then you'll have to go through all of those as well.
Yeah.
And so I think that is a bridge of intuition that gives you the eventual time complexity of n by n. Because if you can't assume that you can always add a fixed number, if you're going vertically, a fixed number of horizontal dimensions, then that's the part which instead of becoming plus a fixed number, it becomes times a number. And so another way you can think about it, for example, that I'm imagining, but I don't know if it's exactly correct, but this is the way I'm imagining it as well, is if you have a diagonal, right? So if you have a diagonal structure, then you would alternate the top of the stack being either a row traversal or a column traversal.
Do you mean if like the island was a diagonal?
Yeah, the island was like up down. Okay. was like the 0 0 0 1 1 0 2 1 etc. So it was like a staircase, right? Okay. Like we can think of a staircase with some like thickness, for example, right? In that case, when you iterate through the that staircase, sometimes you'll be iterating through the row part, and sometimes you'll be iterating through the column part, right? And so there's no so that way that breaks the assumption that, for example, you can go through all the vertical and all the horizontal ones first or second, right? And so that
Mm-hmm.
dimension, right? That dimension is bounded by n by n.
Yeah, I think like to convince myself of the space on my side, what I'll do after this is just like literally just go through, just like brute force an example of like the island being all land, and then just seeing like experimentally like
Sure,
the that the call stack is actually
you can do
n by
that.
n.
Come,
It's like,
come report back.
yeah.
Oh, cool. Yeah. Anything else? Oh, we can quickly talk about the
Um.
follow up. The follow up one, no.
Oh. What I ended up saying, I ended up like not needing like I ended up like saying something that I didn't need, which is like keeping track of the number of islands in grid one. Like I'm just wondering like why did I say that? Why did I say that?
Well, you probably
I don't, know,
said
I
that.
don't really think too much of it. I was just thinking off the top of my head.
Sure,
Um,
sure. I mean, it still would have been. The thing is, like with that solution, it still would have with what you said. It still would have been correct. It just wouldn't have been necessary, right? In other words, you would have run this island algorithm on both grids 1 and 2 when you only needed to run it on 2, which
yeah,
has still the same complexity technically speaking, but is going to be twice as slow, right? So, so there is a bit of a difference there
yeah.
that you have to be aware of.
Oh yeah,
Yeah. Otherwise, I think you got the idea fine. It's just that, yeah, the initial ideation was I don't think you got fully like clear, but your proposal
yeah.
was fine, um, at the end. Yeah. Okay. Any other questions about that?
No, I think a lot of good ground was covered, and nice to do another rep of these mock interviews again.
Yeah, for
I think
sure.
I've done like four now.
You've
Is it
done a
like
couple, mostly. Yeah, you've done two.
yeah,
The system design ones, right?
yeah? I did like two system design, and then one OOD, and then one lead
Yeah.
code.
Okay, cool. Then I'll catch you next time.
Yeah, thank you very much, Theo.
Take care.